Hello, and welcome to the presentation for the paper Aerial Flight Paths for Communication, How Participants Perceive and Intend to Respond to Drone Movements. My name is Alicia Bevins, and my co-author is Dr. Brittany Duncan, and we are from the Nimbus Lab at the University of Nebraska-Lincoln. We're going to start off with a brief example scenario where we have person A here going about their everyday life, and then a drone enters the scenario and starts moving in a figure 8. What will that person do or think that the drone is doing? And what if that same person is approached by the same drone, but it just moves back and forth in front of them? Will they react differently? As researchers, we want to know how that person is going to act or understand that drone in response to these different motions. This is an essential question that needs to be answered to optimize the chances of a safe interaction for everyone who may come in contact with an unmanned aerial vehicle, especially those who are not as familiar with how they operate. Imagining this scenario leads us into our research questions, which directly are: how do people interpret flight paths, and what do they intend to do based on that interpretation? To try to answer these questions, we embarked on an exploratory study with a total of 120 participants on Amazon MTurk. The first step in beginning this study is to form our research questions in a way that will provide fully formulated, actionable responses. The 6 questions that we begin with are featured on the right side of the screen. The questions are categorized such that the speech questions prompted a verbal request or a speech type of response. All forms of the questions were posed to get a realistic answer to the question of how the participant would expect to perceive and react to a UAV's motion. Here's the overarching picture of what the sections of this project look like. For phase 1, there were 80 participants who were given different combinations of speech, gesture, and action-based questions. Each participant received 1 or 2 free response questions chosen from questions 1 through 6, which are repeated here at the bottom of the screen. The second phase was a refinement phase. We took the exploratory data and analyzed it to inform the third phase. The third phase involved 40 new participants who answered questions 1 and 6 using a forced choice method rather than free response. I'll briefly explain phase 2, and then for the rest of the results, we'll focus on phase 3 in this presentation. Here's a breakdown of phase 2. This phase is an analysis of phase 1. The first method we used was a frequency analysis. The responses from the 80 participants who answered free response questions were categorized by finding most commonly used words and then going back through to group based on intent of words used. Many of the responses involved participants describing the motion in some way, reinforcing the importance of question choice. The second step was the category formation. In addition to states that were consistently reported, we included categories that were relatively low in frequency in the free response, but are states commonly attempting to be conveyed within UAV research, such as delivery. A few examples of categories used are listed here. Finally was an independent categorization. The categories that were just formulated were then presented to 2 raters who categorized the responses. The raters were instructed to choose a category if they believed it appropriately fit the free response answer. They did not have to choose a categorization from the list, but could rather choose other if they believed it was not an accurate fit available. While this method allows for an extra margin of error, it encourages a level of understanding of what intentions people may have had past the use of keyword detection. The raters overall had over 0.93 for kappa agreement scores in relation to these categories, which shows excellent agreement. Through the process of phase 2 and based on the response categorization, we found the need for a physical and a speech-based question. Based on the response categorization, we saw that these 2 questions, 1 and 6, together were expected to provide a more rounded response of what each participant would expect to do and how they would interpret the drone. The full list of options participants were given can be seen on the right side of the screen. Some of the options are similar for both questions as they are appropriate answers for both questions. This is one of the 16 unique flight paths that were shown to each participant. Each video was 30 seconds in length with repetitions of the flight path added to reach the desired length as necessary. Paths were all kept around a speed of 0.5 meters per second. Pictured here, we can see the most popular responses for question 1, which was looking to answer that communication aspect, specifically of what would the drone say to you. From these results, we can assume that participants would perceive a UAV to be blocking a path given large movements across the x-axis with or without movement in the z-axis. Simpler motions with changes to the altitude of the vehicle were clearly understood to communicate landing, but more complex movements incorporating a second direction, such as descend and shift, or axes of motion, such as spiral, were not as clearly understood. These are the most popular responses for question 6, looking for the anticipated physical response. Most popular options were for move away or watch it / look at / stare, with only one deviation for follow it. The rest of the categories were used, but not popular choices. We also used NARS, the negative attitudes towards robot scale, in our questionnaire set. People can then have a positive, negative, or neutral NARS score. Taking a similar approach, all of the possible states, which is to say all of the options they had for both sets of questions, could be roughly categorized into positive, neutral, and negative categories. With this categorization, we saw that people with a negative NARS score were more likely to pick negative states, choosing a negative state 13 times on average and a positive state 9 times on average. Those with a positive NARS score picked negative states 10 times on average and positive states 11 times. Both picked a neutral option around 12 times on average. Briefly talking about the limitations, the main limitation of this work was that it was presented remotely through video. Video is an effective preliminary method of gathering information about how people would expect to respond, but it's not fully effective for seeing how they may actually respond. Since there were minimal restrictions to who could participate, it's possible that many of the participants have never interacted with a UAV before. This could potentially create a gap between their expected reaction and their actual reaction. Also, due to the use of video, we are unable to effectively explore the effect of varying drones in size and sound. There was a reminder at the top of every page to have their sound on, but even for those who did have their sound on, it's highly probable that the sound level varied. Sound can have a significant impact on presence, fear, and interest in the machine, which would be an additional reason an in-person study may be useful. Extending this work as an in-person study could be interesting to compare the results, but would limit our participant pool and accessibility levels. And now I'll cover some specific practical implications for UAV developers and future researchers to provide safe and knowledgeable interactions. First, we saw that complex motions are likely to result in participant intention to move away from the UAV and the area. If you need them to stay and watch what the drone is doing, it's best to minimize the amount of motion or simplify the motion for improved reception. Thirdly, participants report being most likely to follow vehicles with large motions along the y-axis, but only in the absence of altitude changes. For landing, most motions moving down along the z-axis were associated with some type of landing, but had higher agreement with simpler motions, such as descend and shift, diagonal descend, and straight descend. Finally, responses suggested that participants were likely to associate motions of a UAV with gestures of humans, such as nodding for up, down, or a cross for plus. In conclusion, this work presents an exploration into how participants would respond physically, as well as their perception of the messages contained in aerial vehicle flight paths. Secondly, this work suggests that NARS can be a significant indicator of how a person is likely to react and whether they are more likely to expect a negative message to be conveyed. And then lastly, we provided recommendations in terms of specific motions for how people would expect to respond to them. Thank you for watching this presentation, and feel free to email me any questions at the email shown on screen.